Hello, folks. Welcome back to Calculus. I'm sure that this past 2 weeks have not been as relaxing as previous spring breaks may have been. But nonetheless, you've had 2 weeks away from Calculus, and we're going to get back into it, kind of picking up where we left off. And we're going to go pretty rapidly through this beginning stuff, primarily because I talked about it before break, and it also relates a lot to improper integrals, which we just did as well. So the first thing I'm going to talk about is why we're here, right? What's the main thing that we're doing? The main thing that we're doing, again, to reiterate what we talked about before break, is we're asking this question about, does the sum of sequence of terms exist or not? If you added up a sequence of terms and you kept on adding them and adding them and adding them, does the sum of those terms equal some number? And what we say is if it equals some numbers, we call it converging. And if it doesn't equal some number, if it approaches infinity effectively, or maybe even negative infinity, we call it diverging. And the first thing we talked about was that we said that the sequence, right, the sequence of terms needs to be approaching zero in order for us to actually have a chance of converging. We talked about this before break. And the way we wrote this was that we said that if the limit as n approaches infinity of a sub n doesn't equal 0, then the series must diverge. And the reason that we said this was that if you're just say you added this, right? Here's an example, right? 3/4 plus 4/5 plus 5/6 plus 6/7. You might be saying to yourself, hey, that's getting closer and closer to 1, right? Look at that. It's getting really close to 1. I mean, if you went out really, really, really far, you'd be like, yeah, I have 10,000 over 10,001. I mean, that's getting close to 1. The problem is you're just going to keep adding, you're going to be adding ones forever, right? You're just going to add ones. And therefore, that sum, right? If you had to think about the sum, it's going to diverge, because there's no way that this can approach some number. It's going to keep on going and going and going. You can just add 1 and add 1. The only chance you have of converging is if the series the sequence approaches 0. That's the only chance, right? So let's talk about the other one that we talked about before break, which was the infinite geometric series. Infinite geometric series, they kind of look like this. I like writing them this way. You may have read it, last year. You may have done it this way. It really doesn't make a difference. They're both the same thing. But here's this idea that you have this common ratio. And if you have a common ratio, what we talked about is common ratio R. Put a little space in there. And the common ratio R, what we talked about was that in the event that R, the absolute value of R was less than 1, then the series converged. But if the absolute value was greater than 1, actually greater than or equal to 1, if it actually equals 1, it's not really a geometric series. It's just the same term being repeated. But so I guess I should start numbering these guys. I'll start numbering these tests. We'll call this test number 2. So if it follows one of these forms, right, if it's a geometric series and the common ratio, the absolute value of the common ratio is less than 1, then the series converges. Vice versa, if the absolute value of R is greater than or equal to 1, then the series diverges. Okay, so that's stuff we've done before. That's stuff we're going to use. Things that we're now going to talk about based on improper integrals are these next 3 tests, effectively. The first thing that we're going to talk about is the P-series. And if you're wondering why the P-series is true, I'm going to talk about it next time I chat with you. So just, you can look it up if you'd like. If not, we're going to talk about it when we talk about the integral test next. But for now, what we're going to talk about is the fact that if, put it 3, if it is of the form, again, this could be 0, it could be 1, it could be any number really there. But if you're of this term, right, that's a p-test where you have 1 over n. I mean, an example of one could be this, right? 1 plus 1/8 plus 1/27 plus 1/64 plus 1/25. You get the picture, right? This is the sum from n of 1 to infinity of 1 over n cubed. So that's one example of one, right? It's where you're going up, the denominator is increasing by some power every time. This, what we talked about when we did improper integrals, holds true for the series as well. And what we said is that if this p was going to be less than or equal to 1, then just like the integral diverges, the series diverges. And vice versa, if it's greater than 1, the series converges. Again, I'm just piggybacking off of what we did in improper integrals. I'd be going much slower if we didn't do all these improper integrals. So say you have some series. I guess I need to be careful about this too. I'll be careful in a second about this. Say you have some series a sub n. And it is always less than or equal to. Actually, hold on. Let me change that a little bit. Yeah, let me change the writing of this because the series doesn't really matter. It's the sequences that matter. So say you have some sequence a sub n, right? And it is always less than or equal to b sub n. Another way of saying is that it's smaller than b sub n. Okay? And so that you have some two sequences, right? A sub n is one sequence, b sub n is some other sequence. If we know the sum of a sub n diverges, then we know must diverge as well. Why? Well, if this sum here is so big that it's not approaching something, and this guy here is always bigger than it, well then guess what? It's not approaching something too, right? This is going to infinity, like this could be going to infinity, then this must also. And now, obviously, let's switch it up. So now b sub n is smaller all the time. If b sub n is smaller than something that's converging, then sure enough, b sub n must converge as well. Just like when we did improper integrals, this is called the comparison test. So we have a p-test up here, and then we have the comparison test. So number 1 is the divergence test. We check to make sure the sequence is approaching 0. Number 2 is the infinite geometric series test. We see if it's an infinite geometric series, if the r, the common ratio, has an absolute value that is less than 1, we know it converges. We know the p-test, if the p is greater than 1, the series converges. And now we have the comparison test, which says that if you are bigger than something that diverges, you diverge too, or if you are smaller than something that converges, then you converge too. Okay, so they're the first 4. The 5th one, and by the way, the 5th is not the last one. We're going to do another 3 tests after this as well. But the 5th one's the last one for today. And you probably can see what this one's going to be. But what we talked about before, very similarly, is going to be the fact that, again, we're going to have 2 sequences. And we're looking at the ratio of the terms of the 2 sequences. So sequence 1 is kind of a sub n, and b sub n is sequence 2. And what we said is that if these 2 are approaching some number, right? Let's call this some number, I don't know, let's call it c. Okay. If the limit exists, okay, if the limit of a sub n over b sub n, so let me write f. if the limit exists of some term over another term exists and c doesn't equal 0. So it has to exist, right? Here, look, it exists. And c sub c doesn't equal 0, then a sub n and b sub n converge or diverge together. And this is called the limit comparison test. Now, one thing that I kind of didn't spend too much time talking about because I'm kind of trying to do a blitzkrieg approach as quickly as possible. One really important condition for all the tests on this page, the PE test, as well as the comparison test and the limit comparison test, they all are dependent upon this one condition. And they all are dependent on, so all these tests are dependent upon the fact that they are always positive. Dependent on that these sequences, I guess, the sequences are always positive. In math speak, that says for all n, a sub n and b sub n are greater than 0. And that's important because we're going to talk about shortly, in the, I guess, two times away from this, is we're going to talk about times where they don't actually converge. When they don't actually stay positive and they might alternate signs. So I'm going to stop here for now. I'm going to give you a couple example problems so you see how these are applied, and then we'll talk later.